Software Engineering Radio, Episode 59, Static Code Analysis. Okay, welcome listeners to this new episode of Software Engineering Radio. This episode is about static analysis, techniques, concepts, and tools, I guess. And to do this, we have a guest, and this guest is Jonathan Aldrich. And before we talk about the topic, I think, Jonathan, it's a good idea that you introduce yourself and talk a little bit about your background, what you do in real life.
All right, thank you. I'm an assistant professor at Carnegie Mellon University, where I do research in the area of static analysis, programming language design, and also teach classes in the area of static analysis. And this material is actually from a tutorial here at UPSLA, but also from some of the classes that I teach there.
Okay, so I think to get started, we might want to discuss why you would want to do static analysis and what it is actually. So give us an introduction to the topic.
So static analysis is basically what I like to think of it as a way of exploring the different ways that the program might execute in an abstract way, typically. You can look at testing as a point of contrast. Testing will go through and execute the program with a number of concrete inputs, and your goal as the tester is to exercise the program in many different ways to try to see what it does and see if in particular it does what you expect it to. Static analysis is taking a different perspective on this. Instead of taking particular concrete executions, it will execute the program in more abstract ways and examine it for generic kinds of flaws. The advantage is with the abstract program exploration, you can find a lot of problems that you wouldn't necessarily find with particular concrete executions because you have to find the right one, essentially.
You don't think about using the correct input values in order to cover this kind of problem.
Exactly, right.
So what kinds of errors can you actually find using static analysis? Are there particular types of errors that can be easily found, others can't?
Well, there's a fairly broad range of errors static analysis can find. Right now, security vulnerabilities are a critical issue for a lot of companies today. Things like buffer overruns, unvalidated input, which could be tainted data, or attacks for SQL injection, command injection, cross-site scripting. Memory errors are another common programming error that impacts reliability. Things like nullity references, accessing uninitialized data, memory leaks, issues a lot of developers grapple with that are often difficult to find using testing and inspection and other kinds of techniques. Those are typical ones, but there's a lot of other possibilities people have been looking at from the research point of view. Anything from how do you use an API or a framework to looking at exceptions and their flow through the program to even looking at design kinds of issues such as violations of encapsulation, etc.
And so to just get this straight, this kind of static analysis is not about coding conventions and capitals versus small letters in variables. It's really about semantic analysis of what the program does and not about trivialities.
In the best case, yes.
Okay.
There are certainly one can use static analysis to enforce sort of formatting and coding conventions, and people have used that in certain environments where they feel strongly about those constraints.
Mm-hmm.
But I think the real value of static analysis comes in looking at the kinds of issues that humans are actually not very good at assuring. You can do a code review and you can find lots of style issues. But a code review may find it very difficult to find a memory leak because to understand the code you're reviewing, you need to know the context. Who allocated this memory? Who's responsible for freeing it? If I let a pointer drop on the ground, well, maybe I'm not the one responsible for it anyway, and so maybe that's okay. I have to know the context, and the context is the most difficult thing to get in the context of, say, a source code review.
But how do you actually know this context? I mean, typically code is called from many different parts of the system under certain partially convoluted conditions. How do you actually find out the context in static analysis? Does it actually work?
Well, I think that's one of the big challenges in the design of static analysis is how you find the context. And there are many technical approaches. They fall into a couple of categories. One is simply exhaustive exploration. If you were, as a code reviewer, you could find out the context just by reviewing all the code around. Now, you don't have time to do that, but a computer may have time to do that. Certainly, it has time to look at all the code because it's compiling all the code anyway. In cases where the context is more interesting, you may have a lot of challenge figuring it out just by analyzing the entire program at once, because it requires essentially inferring the programmer's intent. A good example is a concurrency analysis. To get concurrency right, typically the way programmers will make it work is they associate each bit of state with a lock, and they hold that lock before they access the state, right? Not the only way of correct concurrency, but a very common one. To assure a program, you have to figure out what's the association between locks and state. That's something that is very difficult to infer automatically. But in that case, having the programmer help you out a little bit can make the static analysis much more effective.
Having him help out, like annotating the code or having some meta information that is passed to the tool?
Precisely. Writing little annotations that talk about, for example, what kinds of locks are associated with what kinds of objects can give the tool just enough information to then check the consistency of locking from that point on.
So that is probably in line with some of the some JSR in the Java world, where people try to define that certain variables must not be null. Never, ever. They're not expected to be null. And then you can have some kind of analysis tool that verifies that the variable isn't ever null.
That's right.
Once it's dereferenced, of course.
So this is an ideal match for the kinds of annotations that have been added to Java and .NET recently. And I know there's a JSR specifically looking at annotations like not null. And I think they're thinking of locking issues as well in that context.
Yeah, yesterday I was in the tutorial by Brian Getz about Java concurrency, and he said he showed this additional annotation on a member variable that says guarded by such and such. But the problem is that this is just documentation, so there is no easy way of finding out whether, when you access the variable, the lock is actually held. And my thinking in that context was that maybe one of the problems is that today's languages aren't declarative enough. You have a lot of behavior, in more or less understandable and obvious lines of code that lock or don't lock. So would you agree that maybe making languages more explicit about certain things such as concurrency, that this would make such analysis things simpler to implement?
I think that's absolutely true. In fact, if you look at concurrency analysis in Java, it's considerably easier than concurrency analysis in languages like C++, because Java has a built-in synchronization construct. And so a single analysis can build in the concept of synchronization and check the common idioms that people use. Now, of course, one doesn't have to use the synchronization statement bare in Java. One can use library abstractions for locks like the ones that have recently been added to Java. And of course, that only makes concurrency checking more challenging. Mm-hmm. But certainly raising the level of abstraction can help the analysis.
Okay, but you were talking about idioms and conventions that are documented. That brings up the question, how many false negatives do you actually get? I mean, people might use a convention 90% of the time, but in the rest, the code may not necessarily be wrong. They just weren't using the conventions. And this is one of the things that has given static analysis a bad name sometimes, by saying it sort of reduces the things you can actually do. It forces you to code in a special way. Is that still true?
I think that's clearly one of the big challenges for static analysis. And I think, in a sense, it's a fundamental limitation because the static analysis, all static analysis basically is looking for some kind of pattern of correct usage. And if you have what's called a sound analysis, one that will tell you of any error in a particular category if there is such an error in your program. It has to find particular patterns that are reasonable to check, right? The analysis will terminate and give you a response in a short amount of time and so forth. But unfortunately, then, of course, as you said, there are other patterns that could be used that you don't encode. Now, I don't think this is necessarily a huge problem in principle, because I think human engineers work the same way, right? I don't know very many human engineers who reason about a concurrent system by actually considering all the interleavings between threads that are possible and whether any of those could lead to a problem.
That's true,
right?
yeah.
They actually use these higher level patterns themselves. And so while it may take us some work to figure out what all those patterns are that engineers are using, if we can do that, then I think we can get an analysis with acceptably low false positive error rates.
Yeah, that sounds reasonable.
The other thing from a software engineering point of view, of course, is that there's nothing, if there's parts of the program that you can't assure with static analysis, don't try to assure them necessarily with static analysis if you need to do things a different way. All that means is that, maybe for your reviewing or your testing methodologies, you spend a little more time in that part of the program. And the static analysis reduces the effort you have in the rest of the program.
Yeah, so you find the stuff that static analysis is good for with static analysis, and you have more time for the real hard problems.
That's right. I think the best use of static analysis in an engineering context is to marry what computers do best, which is being very thorough and complete in their checking, with what humans do best, which is the insight behind the correctness of the program that might be expressed in annotations or might be put to work in these detailed examples or patterns that perhaps the static analysis might not catch.
Yeah. So how does static analysis actually work? In the slides that we were using as a basis for this interview, I see terms like termination, soundness, and precision. It seems like these are the core concepts in implementing such tools. Do you want to elaborate a little bit about these, maybe 3 principles or whatever you call these?
Sure. These are qualities one would like to have in a static analysis. Termination, obviously, you want it to run you won't want it to terminate ideally in a reasonable amount of time. You'd like your analysis to be sound and that it doesn't miss errors, because the real strength of computers, of course, is their exhaustiveness. And so while not all analysis can be useful without being sound, it's certainly a desirable characteristic when you can get it.
Yep.
Precision is the last one, and this goes to really the cost-benefit trade-off. Your static analysis is going to tell you a lot of errors. You'd like it to be as precise as possible. In other words, when it gives you an error, you want it to be a real error. So the question is, how do you get all of these? And that goes into the details of how static analysis works. Essentially, the core idea behind static analysis is one of abstraction. You want to take the program and look at the ways in which it can execute, but you want to look at those more abstractly. An example might be, let's see, say you were doing an array bounds analysis to avoid buffer overruns. You might try to keep track of variables in the program that might be indexes into the array, for example, and whether each one of those variables is less than, equal to, or greater than the bound of the array. And so your abstraction might be a very simple abstraction, and a realistic checker would actually use more interesting ones. But let's pick this one for just as a simple illustration. So you've reduced your variable, which might be an integer with 2 to the 32 states, right, to just 3 states, less than, equal to, or greater than.
So basically, you're keeping track of the values of all variables that might be used as indexes, and then you keep track where they are in this range statically.
That's right. And what you do is you essentially execute the program, and you look, given the state of the variables in the previous state and the integer expression, what can you tell about the states in this abstraction in the next state? Okay?
Okay.
And you propagate that around the program until you've seen all the different states of the variables and all the states they can reach at every point of the program.
Okay, but still, isn't that a problematic abstraction, given that you might add indexes or add variable values to indexes? So if you only know it was less than the maximum possible value, and then you add 5, you don't know anything about it.
Right. So this goes exactly to the problem of abstraction, right? Because when we abstract, we lose some information. And that's both the strength of static analysis, because abstraction is what allows us to be exhaustive. Essentially, we've reduced the essentially infinite number of states in a real program to a finite number of states, which means we can now explore them all in some sense, right? So we can be complete and exhaustive. But we've lost a lot of information about the details. And so, as you say, as soon as we add a constant, we might lose all information about the range of this thing, and we might get a false warning.
Yeah, I guess the key thing here is to find the right abstractions, and that's probably where the tools need to be smart, where lots of experience goes into how the tools actually choose their abstractions.
Exactly. So a more realistic abstraction, although one that's also more computationally expensive for this example would be Pressburger arithmetic, essentially addition, multiplication by constants, because that's a kind of arithmetic that is expressive enough to represent a lot of the things you actually see indexing arrays. Maybe not complicated multidimensional arrays, but fairly simple arrays you can express with this. And the big benefit is that it's decidable. So you can run an analysis that will terminate and give you a response, and it's also abstract because it doesn't look at one particular execution. It looks at the relationships between variables mathematically or algorithmically, and so it can see if there's a corner case that you might otherwise have missed that is an error.
So again, to look at this from another perspective, is it fair to say that one of the main problems is that programs as we use them today don't necessarily represent the intent of the programmer, so you have to kind of reverse engineer what the programmer wants to do in order to limit the state space in which the program should or can be?
Yes, I think that's exactly what a lot of analysis is trying to do. It's trying to, the engineer wrote the code, and they were probably thinking about the correctness of issues like lengths of arrays and null pointers and memory dereferences, and they probably had abstractions. The problem is, of course, some of those might have been wrong. And so what analysis is trying to do often is reconstructing those, sometimes with annotations from the programmer, sometimes more automatically, and then verify them. Of course, you could say, well, let's just put all the intent in the program. But, of course, expressing intent is expensive.
Yeah, but
so you have to choose a compromise.
Right, but so just to compare this to other validation approaches, if you consider like the model-based world where people use formalisms such as state machines or Petri nets to express behavior and maybe some higher level constructs to describe dependencies, you can then run the analyses on model level, and because they are less cluttered with detail and more related to the actual problem domain, so they represent the intent better, you can probably more easily do these kinds of analyses. So the central challenge, or the reason why code analysis is probably more complex, is that these domain-specific abstractions aren't there anymore. You have reduced things to a very low-level way of expressing things, so you have to reconstruct all these things.
Yes, I think that's absolutely true. And where you have a higher level model, there's a lot of benefit from applying analysis at that level of abstraction as well. I think the challenge is that not all programs, not all domains can be captured in these simple sort of state machine-like abstractions, right? At some point you need Turing completeness. And then at that point you have to bottom out in code, and what are you going to do? You're going to need some kind of analysis.
So assuming that we have actually, left this model level of abstraction and gone into the code, then we have things like conditions and loops and things which sort of make the number of cases, the number of paths explode. How does static analysis deal with these cases? Well, with the intention of terminating in a finite time.
Absolutely, and this is one of the major challenges. So the key is, it goes back to abstraction. If you think about analyzing a loop, one thing you might do is run through it once, run through it a second time, run through it a third time, and gradually explore all the paths. But of course, you don't know when to stop, because there could be an infinite number of times through the loop. The trick is when you're actually analyzing program variables more abstractly, you only have a finite number of states the program could be in. And so your index, which is incrementing, +1 every time you go through the loop, Now, it only goes through 2 or 3 states. And now, when you go around again, it's in one of the states it's been in before.
States at this level of abstraction you introduced given your understanding of the program.
Exactly. And your understanding of the problem you're trying to check, because the abstraction you use for array bounds may be completely different than the one used for concurrency. But the abstraction is key, because once I come around the loop and I've already been at that point in the loop at that state, then I know that even though the concrete program may go through the loop many more times, it won't change what I know about the values in the abstract space any more than it already has. And so I can stop my analysis, but still represent all the possible executions that may have gone through the loop many, many more times.
So the key again is to find the right abstractions, or even to have a tool that finds the right abstractions from the source code, extracts them, and then partitions the cases and the paths according to these abstractions.
Exactly, and a lot of recent state-of-the-art research in static analysis has been looking at novel abstractions, novel ways of representing abstractions, ways of inferring, as you said, abstractions automatically from the source code.
Does that actually work in practice? I mean, in a non-trivial system for a number of cases that actually is useful?
Absolutely. So one of the key ideas in a recent static analysis is the idea of counterexample guided abstraction refinement. It's a mouthful, but the idea is that it's a way of finding precise abstractions automatically from program text. It's used in most notably perhaps in the Microsoft SLAM tool, now part of the static driver verifier, which you can download from the Microsoft website if you're building device drivers. It's a tool basically for encoding device driver rules and making sure you write those drivers correctly. But the internal piece of how abstraction works in that tool is very interesting. The basic idea is you start with an abstraction that isn't really tracking very much about the program. Maybe you're looking at whether you acquire and release a lock, and you discover there's a path through the program where you lock the lock and then you go and lock it again. And that second time would be a deadlock in some implementations of locks, right? So that would be an erroneous path. But it turns out that if you reported that to the user, in some cases it might be a false positive, right? Because it might be that those are both in an if statement, right?
Okay, I see, yeah.
If you take one branch, then you're never going to take the other branch, and so you're never actually going to lock it twice in a row. So the idea in counterexample guided abstraction refinement is from this error path generates a counterexample, essentially a place where there's it generates a path through the program that exhibits this error. What you can then do is do a different kind of analysis that symbolically executes the program along that path and sees if that path is actually feasible.
I see.
And you might discover, there's this predicate that says, this flag that means I can't go both places at once because I check flag is true on one path and flag is false on the second branch, right? So in that case, that tells me this flag is an interesting piece of data that I should be tracking. And now I'll do the analysis again and I'll track the value of that flag and I'll discover, there's actually no error in this code. So that's a way of discovering abstractions automatically.
Do you have some kind of numbers, an impressive case study where you can say, there was this project or development team and they had so many bugs and then they used static analysis and the world was so much better. So is there something you can, tell us off the top of your head that convinces listeners that this is really something that is working?
Well, I think Exhibit A for me is the way that Microsoft has used static analysis in their development of the Windows process. Manavir Das, originally at Microsoft Research, has recently, in the last year or two, led a team developing static analysis for the Windows team. And they've applied a lot of these ideas to some of the most vexing bugs that Microsoft exhibits. Things like buffer overflows in terms of security holes, other kinds of memory management problems. And they've applied this set of tools comprehensively throughout their process in many ways. So you have to run the static analysis tools before you check in code, and the code actually has to pass the static analysis before you can check it in. So it's a part of the process there. There are other analyses tools that run over the main branch of the source code for Windows and generate different kinds of errors. The great thing is, if you're Microsoft and you're really sick of shipping out a bug fix every month, right, on a particular schedule, right? It's just not good for your image, and it costs your customers thousands of dollars and millions of dollars in time to upgrade their software, and even more when an actual bug escapes and gets out in the wild, right? So you're very motivated to fix these, and static analysis, I think, is giving them the potential of reducing those dramatically, even to zero in the case of a sound analysis for classes of errors that can be checked this way.
So Microsoft actually uses this approach today in all of their products, or?
I don't have information to say all of the products, but I know the Windows team. I know everything filters within that organization from the Windows team to other parts. So I would expect Office is using these tools and some of the other teams as well. And are these tools available for everybody to use? Some of those tools are. There's a tool called Prefast, which will run on your desktop. It's included with the Team edition of Microsoft Visual Studio 2005. Yep. Prefast is also available as part of the Windows SDK, which you can download even without if you don't have the Team edition of the Microsoft Studio tool. So that's something you can use. And what's interesting is that the buffer overrun checker actually uses the same ideas that I was talking about in terms of expressing design intent in your source code. Yep. There's a language called Standard Annotation Language, or SAL. This was developed at Microsoft and is used by Prefast, in which you can associate, say, the length of an array you pass to a function with some other parameter that you also pass to that function. And then the analysis uses that little piece of design intent to check the function and make sure that any array accesses within the function are consistent. Okay, so after talking about these conceptual issues and the theory, so to speak, let's now move to practice, in the sense that you probably have a good overview over the tools that exist for the various different platforms and languages. So do you want to give our listeners a quick overview of which tools exist and maybe what are the characterizing features? And we'll put the links to these tools into the show notes, of course. Certainly. I think one of the most exciting things today is that we are seeing more of these tools come out and be available to developers. And they range from open source tools that you can download for free to desktop tools like Prefast that you can, and the static driver verifier that you can download from places like Microsoft, to enterprise scale analysis tools that are packed with a wide variety of other features. So I don't claim to be comprehensive, but I'll tell you some of the tools that I think are the most prominent in this space. I think in the open source world, Findbugs may be the most prominent. It was actually published in OOPSLA a year ago. As the name suggests, it's looking at bug finding. Their slogan is "Finding bugs is easy," and they have some data to back that up. The great thing about Findbug is obviously it's free. There's a large community that's contributed to it. And the big thing for an organization is that you can go ahead and adapt this to your process, your set of tools, whatever they may be. You can customize it with analyses that you write yourself. And that's a real value, because a lot of the biggest bang for the buck is taking those ideas, those concepts that are most important, with a set of libraries you use, the set of coding idioms and patterns in your organization, the set of problems in the domain you're facing, and write static analyses, simple ones that capture those kinds of problems. Findbugs also has a very large selection of already built analyses, generally fairly simple analyses. This is not going to find. They're the kinds of bugs I mentioned earlier.
Okay.
In terms of array bounds errors, memory errors, simple kinds of concurrency errors. What's interesting about find bugs is that they tend to be very local analyses. Local meaning only analyzing within a procedure or within a small snippet of byte code.
And by the way, it's for Java. I think we didn't say
and
that
it's for
yet.
Java, yes. Yeah, that's a very good. Other tools for other languages, perhaps, but. So you're not going to find some of the really deep bugs that reach across procedures and so forth. Although it could potentially be extended to some of those.
Okay.
But I think there's a lot of value to be had potentially there.
Okay.
In the world of commercial tools, there's a set of a number of tools that are really aimed at the enterprise. Coverity is one that builds on some research coming out of Stanford University. Some of their strengths are focus on C and C++, low false positive rates. They're not going to waste your time with a lot of error messages that are bad, that are useless.
Yeah.
Another one in kind of the same space is Grammatech Code Sonar, C, C++, and Ada.
Ada, okay.
Yes.
Still around.
That's right. And it's surprising. There's a number of static analysis research that's done in Ada. Spark Ada is another tool I've heard of. I don't know as much about.
One of the reasons is probably that it's easier to analyze than C++, I'd guess.
Well, I think in the same vein as Java, it's a statically typed language with more reasonable semantics.
And the other reason might be that it's used a lot in these safety-critical environments, like in the military area, where validations are probably even required sometimes.
That's right. And indeed, listeners who are building embedded systems may find that the quality constraints of that domain are such that static analysis becomes even more worthwhile. So a lot of these tools actually have significant constituencies in that area.
Yep.
Clockwork is another tool in the space. Clockwork focuses, I think, equally on security and bugs. They have C, C++, and Java support. And they talk a lot about support for enterprise, tracking bugs over time, some architectural visualization, which I think is a nice feature to prevent bugs from coming in the future, as well as ones that are there right now. Looking at tools more focused specifically on security, although they'll find some coding bugs as well. Fortify and Ounce Labs are both in this space. Fortify actually has a strategic relationship with FindBug, so I don't know. There may be some coordination coming there at some point. Fortify will handle C# as well as C++, and Java, and some web and database languages. So a lot of cross-platform compatibility there. For embedded systems, as we were mentioning before, there's a tool called Polyspace, which is more specifically focused on embedded systems. They support Ada, as you see. And they'll be focusing on some issues like integer over and underflow, which might sort of fall below the radar on a lot of systems. But if you have an embedded system and you don't want your rocket to go off course, then that's a critical issue for people in this domain.
Yeah, and for those who don't know, this is a real case, right? So
that's right.
I think the Ariane 5, that was the problem there.
That's right. So Polyspace is may have the answer there. And of course, when you're in the embedded space, some of these vendors will err more on the side of reporting more possible warnings. At the expense of having more false positives.
Which is probably a good idea for safety-critical things.
Exactly. And so I've talked with people in Polyspace, and they say, this is a trade-off that we've explicitly taken, which is exactly the right thing for the domain they're targeting. But it's a trade-off you have to make based on your specific needs.
But when we took a look at quite a lot of static analysis tools that are targeted at finding bugs, there are also static analysis tools that are targeted at sort of helping you visualize, understand the design, the architecture. It's both called static analysis. Are there relationships between the tools, between the companies? I mean, the target is obviously different, but still.
Yes, I think it's certainly true that some of the same techniques apply. Grammatech, which I already mentioned, has some support for, say, visualizing the in their Code Surfer product. They have support for looking at the aliases in your program, the runtime heap structure. There's also products that are looking more at software architecture. Two of those are LaTeX, which is takes the idea of design structure matrices from engineering practice in many different fields, and will show you the degree to which your system follows, say, a layered architecture.
I see. Yeah.
Basically, they'll lay out your modules at a high level of abstraction along a couple of axes, and show you at intersections in those axes where one depends on the other. And if you can lay out those modules so that all of the interactions are along the lower left of a triangle, for example, if you can visualize that, then you have a layered architecture. But it can be very interesting to see where, say, cycles in your architecture are, because those might be points at which things might be more difficult to evolve, or there might be more dependencies.
So this sounds to me a little bit like this heuristic stuff, like cyclomatic dependency and all these kinds of things. Again, that's out of the scope of what we've been discussing today, but that's another way of analyzing software, but not for bugs, but rather for maintainability, complexity, and stuff.
That's right. And heuristics, one always has to be careful with heuristics, because one can optimize the heuristic without optimizing the code itself. But they can also point you to places where you might want to look more closely.
Yeah, but I think there's a similarity here to actually finding bugs by making assumptions about patterns of usage, because that's also heuristic in a certain way.
Yes, that's true. I think one could point to a difference in that one can validate that certain patterns lead to actually prove that there are no bugs in a system, right?
Yeah.
Whereas metrics such as cyclomatic complexity are not directly related to correctness in the same way.
Or even quality.
Right. But there certainly is a relationship in that understanding the way engineers typically build software and the way good software is typically built is a thing, requires understanding the patterns of usage at a deep level.
Okay, so now that we took a look at the tools, how do you actually go about introducing static analysis into your company, into your development teams?
Well, I think that's a very tricky question, because there's a cost to using static analysis tools, right? The cost of running them, the cost of paying for them, but most importantly, the cost of engineer time looking at the output, seeing if these errors are real, and sorting through the false positives. And so it's important to be very careful about how to introduce this. I think a big part of it is choosing the right tool, choosing a tool that's well designed, that fits the needs of your organization, and actually doing a little bit of customization to making it fit in. If you take FindBugs off the shelf, for example, you'll see there are literally hundreds of checkers in there. Many of those may produce false positives for you, either because you don't care about them, they're not a problem in your domain, you commonly use idioms that don't match what the analysis is looking for.
Can you give an example? I thought a bug is a bug, no matter what the context.
Well, errors in using concurrency are not bugs if you don't have multiple threads in your program, as a perhaps trivial example.
These checks sort of assume that there are several threads without checking that the threads are there, and then saying if there is a second thread calling the same method, then there would be a problem. That's
right. Well, especially for a very simple kind of analysis that just looks very locally, it may not be aware of whether you're actually in the context of a multi-threaded system.
Okay, I see.
There's certainly many more examples, but some of the things that FindBugs might check for might just be generally considered bad practice, but perhaps in your specific setting, it's not an issue. Or you may disagree with the authors of the analysis about what's good and bad practice.
Okay, so again, this is about heuristics, which are also always sort of subject to opinion.
In some cases, yes. So, but what you'll find is the typical pattern of an organization is they'll take an off-the-shelf tool like this, and they'll have to say, these are the analyses that are really the points of pain for us. Those are the ones we're going to turn on. Those might even be the ones that we integrate into our process in some way, like saying all of these must be dealt with before we transition from coding to testing or testing to release.
Yeah, so again,
in the software lifecycle.
Sort of standardizing the usage of the tool and integrating it into the enterprise-wide processes.
Exactly. Another piece is really winning the hearts and minds of the developers, if you will.
That's important. Yeah.
So starting with a core team of developers who are willing to experiment, try out something new, given a little bit of leverage, leeway from management, and get the tool working well with those developers, and then use those as evangelists in the rest of the organization. For a large organization, you're not going to be able to push something like this strictly from the top down.
Yeah, I see.
It has to work well, but you also have to get some people behind it that are willing to say, hey, look, I've been coding here for 10 years, and last week the static analysis found a bug, a buffer overflow, right, in critical code that I introduced 5 years ago. And, let me tell you, I didn't want to wait until the hackers found that one.
Great, yeah.
It's a time bomb. So I think stories like that, when you find analysis and it's it's really focused on the issues that are critical for your company, for your setting, that's when you're going to be able to sell it. And that's where you can really justify the cost and the investment in this technology.
So sort of get buy-in of some developers and have them tell the others how great it worked.
Yeah, that's right. I think what excites me about static analysis is that the technology is just getting to the point where we can address some really deep problems. I give the example in my tutorial of the Fluid Research Project from Carnegie Mellon, which is focused on concurrency. Yeah. Concurrency is notoriously difficult to deal with.
That is certainly true.
And it's because everything is non-local. You have interference between threads running in different parts of the program. You have this complicated design intent relationship between locks and objects that you have to track. And if you have a bug, you may find it. You may run 1,000 tests and not find it, but you deploy your software and it gets hit 1 million times a day, and now it happens every couple of hours.
Or it happens in the release version, but not in the debug version, and all signs of width. Yeah,
that's right.
That's why we have this term of the Heisen bug. You might have heard about
yes.
it. the trying to measure the bug changes the bug itself.
Exactly. So this kind of error is exactly the one that static analysis is good at applying, and the Fluid technology is being actually commercialized right now. Hopefully, you'll be able to buy it from a company called SureLogic in the near future. But I think we're seeing from that and from some of these commercial companies, from the experience at Microsoft, static analysis is really maturing. It's becoming practical. It's hitting the problems that are really hurting development organizations. And I think within the next 5-10 years, we're going to see it become a ubiquitous part of the quality assurance landscape.
That sounds really cool, because it sounds like it should be very helpful, very useful, and once the false positives and false negatives are reduced, it sounds like there's no downside to using it, actually.
That's right, and it's not a silver bullet. Quality assurance is always going to be hard.
Sure.
There's something we should talk briefly about is actually the applicability of static analysis. There are problems to which it's very poorly suited. Problems where the property you're trying to assure doesn't fit into a well-defined pattern that works across many programs and is sort of worth compiling into an analysis. Classic, UI testing, functional. Does it give me the answer I wanted? That kind of testing.
Yeah,
We're not going to replace that.
Conformance to the requirements. Does it look like users want it to look? Is it well usable, intuitive, that sort of thing? Obviously.
Exactly. But we already have testing and review methodologies that are very good for assuring those kinds of issues. What we don't have is ways of addressing these kinds of memory errors, concurrency errors, these things we're seeing static analysis really
in the low-level technical domains. The computers have their strength, obviously, rather than humans. We tend to lose our way there. That's true.
Exactly. And so I think from that perspective, static analysis is really filling a hole and has a potential in those areas to increase quality very substantially.
Yeah, and I think this people are always asking for the killer application of a new technology. And I think for static analysis, this killer application is probably going to be if you can detect meaningful, complex concurrency problems, because they are as we all know, really, really tough. So if the tools get to a point where they can help there, I think that will be the argument of introducing these types of tools into the process, especially since everybody has to deal with concurrency now because of all those multi-core CPUs.
Right. I think it's a issue, as you say, that's only going to increase.
Okay. Thank you very much for talking to us about static analysis, and thanks everybody for listening.
Thank you.
Thanks for listening to Software Engineering Radio. If you want to get more information about Software Engineering Radio, or if you want to give us feedback, please go to our website at se-radio.net. You can also contact the team at team@se-radio.net, although we prefer entries in our comments system on the website so other people can see what you think. Software Engineering Radio wants to thank Henning Pauli for the intro and outro music, as well as Libsyn for providing the bandwidth. This episode of SE Radio, as well as all other episodes, is licensed under Creative Commons license. See the Software Engineering Radio website for details.